Alright, I'm going to be going through problem 32 in chapter 6. It's a two-circle problem, whatever that means. I guess it's moderately difficult. It describes a 6 kilogram block that slides down a frictionless incline that makes an angle of 60 degrees with the horizontal. So it may not be drawing exactly to scale, but it says this angle here is 60 degrees. And it has a block here that has a mass of 6.0 kilograms, and it's going to be sliding some distance down this ramp of 1.5 meters. Hope those are all clear on the picture. The first question asks us to draw a free body diagram. No problem. So we draw our particle here. I'm drawing our block as a particle. There is the force of the ramp acting on the block, which is perpendicular to the plane of the ramp. We also have the weight on the block pulling down. Okay, like so. There is a component, the y component of the force due to the weight that is equal and opposite, and also a force along the ramp that doesn't have any other force in the other direction. It's all the forces, so there's going to be some acceleration of this block down the ramp. And it asks us to find the work done by each force when the block slides down the ramp. All right, so the work done is equal to the force vector, the scalar product of the force and the displacement. All right, the only displacement in this particular situation is along the ramp, and so the work done by the normal force is going to be equal to the normal force, the scalar product of the normal force, and the displacement along the direction, that is perpendicular to the surface of the ramp. All right. Well, even though there is some non-zero, there's actually a normal force of some type. There's no displacement along that y direction, and so the work done by the normal force is equal to 0. The work done by the gravitational force in the y direction is also equal to 0 for that same reason. So this is the gravitational force, the y component of the gravitational force, times delta y. I'm removing the arrows here because this is in a very specific direction, in the y direction, and so that there is no displacement along the coordinate system, coordinate that is perpendicular to the plane of the ramp. So this is also equal to 0, so there is no work done here, 0 joules also. The x component of the gravitational force, however, has some value. The force of the gravitational in the x direction times the displacement in the x direction along the ramp. There is some displacement, there is some force, so we are going to get some actual, there's going to be a value for our work in this situation. We've done this several times, so I'm not going to spend too much time on describing why the angle, why the magnitude, the force along the x component here is equal to mg times sine of theta times the displacement, which is delta x. All right. We can actually plug in all the values for this. That would be the mass is now 6 kilograms, the gravity is 9.8 meters per second squared, sine of 60 degrees, and the delta x is 1.5 meters. So we can plug in the values for this and get some answer in work, which will have units of kilograms times meters squared divided by second squared, which is what joules is. All right, I'm not going to take the time to bust out the calculation, but it's some value in joules. Question B, what is the total work done on the block? Well, the total work, or what we would often call in class the net work, total work, it's the same term, just different words, is equal to the sum of all the other works, right? So what is the sum of the works? Well, the sum of the works is equal to the sum of all of the works by all the forces acting on the block. So we have the normal force, the work due to the normal force, the work due to the gravitational component in the y direction, and the gravitational work done to the gravitational component in the x direction. And so we have 0 plus whatever our value was for the work done, the work done by the gravitational force along the surface of the ramp. All right, so we would just plug in that value, and that's what our total work is, or our net work. In C, it asks us, what is the speed of the block after it is slid down? What is the speed? So we could do a bunch of things here. We could write down Newton's second law and do this like we had done previously. We write down what the Newton's second law is, then we can figure out what the acceleration is, and then we can figure the distance over which it accelerated and figure out the velocity from that, or the speed if we would like. But we've just found out recently that we know that the net work is also equal to the change in kinetic energy. So without going into all of those extra steps of the forces, we can simply write down that the net work is the work done by the gravitational force in the x direction, and that is going to be equal to 1/2 mvf squared, the final kinetic energy, minus the initial kinetic energy, vi squared. In this particular case, it says that it starts, well, it asks what is the speed of the block after it is slid 1.5 meters if it starts from rest. So when it starts from rest, means that vi is equal to 0 meters per second. So if the initial velocity is equal to 0 meters per second, this whole term is 0, and we can figure out what the final velocity is going to be simply by moving across our numbers. We have multiply 2 by both sides to get 2 times the work in the gravitation, or the work due to the gravitational force in the x direction, divided by the mass. Excuse me. And then that'll be equal to Vf squared, and then Vf will be equal to the square root of 2 times whatever the work is done here, gravitational direction, over m. So we can figure out what that quantity is. And had we kept our equation the way it was previously without plugging in all the values, we could actually get some information, right? We could actually plug in this mg sine theta delta x and see that the masses in this particular case would actually drop out if we plugged in that value down there. So you can plug in the number here into this value, plug in the value for the mass of 6 kilograms, and that will tell us what the final velocity is.